This talk is based on, there's a typo, based on the following papers. The first paper is this paper. It's on the archive. It's machine learning, the Sato-Tate conjecture, machine learning number fields. That's the second paper. Third paper was machine learning, arithmetic curves. These three papers are on the archive, and this talk will be based on these papers. All of these are the collaboration with Yang and Tom. The main question can be this. So it is obviously important to develop mathematics for machine learning. And then yesterday we saw some talks about, we heard about this in some talks yesterday. And today we can ask, yesterday also a discussion was arised. So let me just repeat the question. Can we use machine learning to problems in pure mathematics? Yeah, the first talk, actually, the Min-Young Kim's talk was about this. And so in other words, can we develop machine learning for mathematics? That's the main question I want to ask in this talk. And as a test cases, we'll apply machine learning techniques to data sets from number theory. If nothing shows up, then probably the machine learning method may not be useful. But if something works, then we may look at. It's a good idea to look at this machine learning for mathematics. So we'll do this with the data sets from number theory, because we have a huge data in number theory. So more precisely, we'll see whether a machine can learn class numbers of real quadratic fields, ranks of elliptic curves, and Sato-Tate groups of genus 2 curves. So I will define these things in this talk shortly. And I will assume that some of you are non-experts. So at least the first problem will be presented in a very elementary way. As I already mentioned, in number theory, a huge database is available thanks to many number theorists and other supporters. Then the database is called the L functions and modular forms database, or LMFDB. So let us look at the website here. And yeah, there are a lot of things. If you look at this column, the L functions, modular forms, elliptic curves, genus 2 curves, and number fields, and etc., p-adic fields, Galois groups, and some representations and Sato-Tate groups. So you can visit, if you have not done it before, then yeah, I highly recommend to visit this website and look around. So you can basically get a lot of data out of this website. Okay, let me go back to the slide. So because a large set of data is available, we can apply the machine learning techniques. So this website is managed by an editorial board and is funded by NSF, EPSRC, and the Simons Foundation. And it is really useful and well-maintained and organized website. So in particular, data sets for real quadratic fields and elliptic curves and Sato-Tate groups are available. So again, we may download the data and then apply the machine learning techniques. Actually, that's what we did in our 3 papers. So let me introduce real quadratic fields. So this will be elementary, and I just assume that there are some non-experts. So D is a positive square free integer other than 1. And Q adjoint square root of D is a real quadratic field. And as we all know, it is as a set, it's this, and this is a field. And for example, we can consider these things, and then this D can be very large. So for simplicity, so F will denote the real quadratic field. And an element alpha in F is a quadratic integer if it is a root of a monic polynomial, monic quadratic polynomial. For example, square root of 5 is a quadratic integer. And this number, 1 plus square root of 5 over 2, is another quadratic integer because it's a root of this monic polynomial. But this integer, this not integer, but this number is not a quadratic integer because it is a root of this polynomial. The first coefficient is 2, and there is no way to make it a monic polynomial. So this is a non-example. So let us denote the set of quadratic integers in F by OF. Then OF can be described in this way. So it is a lattice like this. And then if D is modulo congruent to 2 over 3 modulo 4, then omega is just a square root of D. If D is congruent to 1 modulo 4, then omega is this. So square root of 5 have this shape of omega. That's right. Okay. And if alpha has a multiplicative inverse in OF, then it is, of course, called a unit. And for example, this number is a unit because it has this inverse, and the number square root of 5 minus 1 over 2 is in OF. And a non-zero element alpha is irreducible if whenever we have this decomposition, one of them is a unit. Okay, so slightly different from prime numbers. Prime numbers are irreducible, but the converse is not true in general. And every non-zero element of OF can be written as a product of an irreducible element of the unit because we can decompose as much as we can, and then we have to stop. But unique factorization may fail. For example, in this field, Q adjoint square root of 10, we have two different factorization of number 9. So the natural question is, when does it happen? So we introduced the notion of a class number of F. It measures how far F is from having unique factorization of every non-zero element in OF. Okay, that's the definition of a class number. It's not the definition, but the notion, basic concept of a class number. And when you say that F is of class number 1, then by definition, F has the unique factorization property. So, and then Gauss studied this before we see examples. Q or square root of 5 has class number 1. This has a class number 2 because we saw number 9 has two different factorization, but the number of factorizations may not be related to the class numbers directly. And then this has a class number 24. And again, this number, this field Q square root of 50,009 as class number 1. So for bit number D, we may have class number 1. And Gauss made a conjecture a long time ago, of course. His conjecture is this: there are infinitely many real quadratic fields with the class number 1. Of course, this is a very fundamental problem, and it is still open. So it's a very important problem, but it's open. And the Cohen-Renstra heuristics predict that around 75% of real quadratic fields would have class number 1. There should be, if the heuristics are, the heuristics say that there are infinitely many real quadratic fields, but we cannot prove it at the moment. Okay, that's the introduction of this Gauss's conjecture. And then we want to see if a machine can learn class numbers. Yeah, that's the question. So we'll have to present a real quadratic field to a machine. And we cannot, it will take a long time to teach all the information, but we'll simply present a real quadratic field by 500 Zera coefficients. And then we'll just show these coefficients to a machine. So what are these zeta coefficients? So if you remember Riemann zeta function, it looks like this. For arbitrary quadratic field, we define dedicated zeta function in this way. So here I is a non-zero ideal. And then we take the norm of the ideal. I will not define the norm. Basically, it's the cardinality of the quotient. And then we take the to the negative s, and then we write it this way. And then these coefficients are the zeta coefficients. Okay, this is the dedicated zeta function. And of course, we can just show D only, but it will be but D itself has all the information, but actually it will be very hard for a machine to do anything with this just D. So instead, we calculate the zeta coefficients and then present a number quadratic field by this 500 zeta coefficients. So we set up the following. So the data set has this many, about 160 or 166,000 real quadratic fields of class number, just 1 or 2. And then we put approximately the same number of each class number. The quadratic fields of approximately the same number of each class number. And then discriminant is less than or equal to 10 to the 6, 1 million. And then we compute 500 zeta coefficients. And then we choose 70% of the real quadratic fields for training, and then 30% for testing. So we have this classification problem. We have this data set, and then we want to see if a machine can classify the class numbers. The machine can tell the class numbers 1 or 2. That's the problem we want to do through machine learning. Any question at the moment? Any question? Okay, so everything is working technically. Okay, good. Okay, and what happens if we apply machine learning techniques? So we apply standard classifiers in machine learning to the data set, so including logistic regression, support vector machine, naive Bayes, and nearest neighbors, and random forest. But we didn't do a neural network or the convolution neural network because we already obtained very nice results, and then we just stopped there. So after training, classifiers could distinguish between class number 1 and 2. So that was an exciting observation. So the logistic regression yielded precision around 0.82. It's good, but not so great. But the random forest classifier produced the best precision of 0.96 with a confidence 0.92, and then it was very surprising. So as you can see, the precision was very high. Actually, it was excellent. Okay. So we apply the same random forest classifier to real quadratic fields with a larger discriminant. So we may investigate if it was an overfitting because we divided 70% for training and then 30% for testing. We didn't think that it's an overfitting, but we wanted to check if the machine or the classifier really has the information about class numbers. So we applied the same random forest classifier trained by the examples, by the data set. Then we applied the classifier to real quadratic fields with a larger discriminants. And then still the classifier shows high precisions. So that was also surprising. So here is the result. Initially, we used this discriminant range. Then precision was this. And we apply the same classifier to this range, so it's much larger. And then the precision was this 0.92. Of course, it went down, but still it is surprisingly high. And then we went further. Now it's it's far away from the original discriminant range, but still the precision was quite high. So that means this classifier has information about class numbers. Okay, that was the first experiment. Any question?
Do you know if the discriminants were prime? Did you take prime discriminants here? Because the two part of the class group is controlled by the number of primes dividing the discriminant, as far as I remember. And I wonder if there's a correlation between what you see here. Are all the discriminants that you took primes?
I have to look at the LMFDB, but right now I don't know. But there is a good like a document about the use of this discriminant and other things. So to make it sure, I have to look at the LMFDB.
Okay. Thank you.
Welcome. I mean, I'm sorry that I don't have the answer right now, but LMFDB, I will have the answer, and I'll check.
Now, as far as I remember, if someone can correct me here, this would be good. The class group has a part which is the 2 CELO group. So the power of 2, which the highest power of 2, which divides the class number, is you can compute it by knowing the number of primes that divides the discriminant. So if the discriminant is divisible by more than 3 primes, then the class number can never be 1. And likewise 2. So I suspect that the discriminants here are usually primes, but maybe they are products of 2 primes if the class number is 2. So this is something that you can check. And that may be a non-random feature that it's conceivable that the algorithm actually learns to distinguish whether an integer is a product of 2 primes or a prime. So that's worth checking. I don't know the answer to that right now.
Okay, thank you for the comment. Yeah, I will definitely check. And then I think there is one more question.
Hi, yeah, this might be pretty stupid, but is there any particular reason for choosing the zeta coefficients for the problem?
Yeah, so we thought that that's the good way of presenting quadratic field. Of course, as I said already, the square root of D has all the information, but that would be too hard for any like entity to immediately tell the class numbers. Then we just calculated the zeta coefficients, because zeta coefficients in principle has all the information about the number field, about the quadratic field. Of course, we have to know all the zeta coefficients, or it may depend on the field. But anyway, so the zeta function has basically all the information about the quadratic number field. I mean, in general, some number fields may have the same zeta function, but in principle, yeah, that has all the necessary information. That was our thinking. But there may be a different way of presenting a number field or a quadratic field to a machine.
So in principle, you could have just chosen a different function as well, right? And got some other 500 numbers.
You mean different what?
You could have chosen a different function and got like different sets of 500 numbers. That would have also worked, right? Like, is there a particular reason why the zeta function is chosen? I'm not an expert, so this might be stupid.
I see. So that's the standard way of presenting an object in object in number theory. So whenever you have an object in number theory or arithmetic, say geometry, you make you pull out some data and make an L function or a zeta function. That's the very standard way in number theory.
Okay, thank you.
Okay, then let me go on. So now let us consider elliptic curves. So let E be an elliptic curve defined over Q. And then, for example, it is defined by this equation. And the Moder-Vaid theorem says that the Q rational points of E is a finitely generated abelian group That means we have a torsion part and this free part, and we have this rank. And then this number is called the rank of the elliptic curve. And there are some conjectures about the rank of an elliptic curve. So for example, it is not known whether the rank can be arbitrarily large or not. So we don't know. The largest known rank is 28 at the moment. At least 5/8 of elliptic curves over Q have a rank 0 or 1. It's the result of Bhargava and Shankar. And question, so basically the rank of elliptic curves, the problem is very interesting and important in number theory. In question, can a machine learn the rank of an elliptic curve? Okay, you can ask this question. So then we will want to present an elliptic curve to a machine. And again, we may use the coefficients of the defining equations, but that may be another, I mean, they may work, but yeah, we decided to use, again, the L function of an elliptic curve. So we define this AP, number AP, by this. It is basically the number of rational points over this finite field. So you take the elliptic curve mod P and then count the number of rational points, the number of roots basically, and then we add this. It's AP. And an elliptic curve E will be presented through this 300 numbers. All these are primes. So the 300th prime is 1987. Okay. And make a data set F consisting of 16,000 elliptic curves of rank 0 and 16,000 of rank 1. And then, so we have this classification problem. We have this data set, and then we want to see if a machine can tell 0 or 1 for each of the data point. Okay. So again, we apply the standard classifiers. And then, surprisingly, logistic regression, the very elementary technique, but very, of course, the most fundamental technique works best with accuracy 0.99. So yeah, we got this result. And here is a summary of the result. We are using the conductor as to control the size of an elliptic curve. And then N is the number of AP coefficients. We train elliptic curves from this range with the 100 L coefficients. Then we obtain this precision. If we use 300 AP coefficients, then we got 0.99. The precision was very high. And then we use the same classifier we obtained here, and then apply this to a higher conductor range, and then still the precision was good. And if you use this, then yeah, again, we got high precisions. So clearly, this summary shows that this logistic regression has the information about telling the rank of an elliptic curve. I mean, for 0 and 1. So there's some, I mean, if you are an expert in elliptic curves, then or it is well known that you may calculate root numbers, because our data set is from the elliptic curves of rank 0 or 1 only. So I showed this result to an expert, and then he mentioned that it is not difficult to tell the rank 0 or 1 because we can compute root numbers. But still, it is interesting that the machine could learn how to tell the rank of an elliptic curve without computing root numbers directly. Okay, let me move on to the next question.
If I may ask another question concerning the root numbers.
Sure.
If the functional equation is odd, then we know that the rank should be positive, and therefore, if it's not 0, it's got to be 1. But in your case, did you eliminate that feature? So, for instance, look. In these examples, is the root number the sole explanation of being 0 or 1, or is it just one of the facts? So if the root number is +1, then you don't know if the rank is 0 or 1, as far as I know. Maybe there's someone here who can correct me. If the root number is -1, then you know that the rank is at least 1. So in your case, it's got to be non-zero. So I'm not sure from what you were saying whether the root numbers are not enough to actually tell 0 or 1, but if you know the root number is -1, you know it's not 0. So that's what I didn't, and I'm not sure that you can actually tell from the data.
So according to the expert in elliptic curves, I'm not an expert. So, and as far as I understand, so -1 to the rank of an elliptic curve rank is this is the root number. Am I right?
No, I don't think so. Okay, I wish there was some. If one of the people listening here is conscious, then maybe then they can say the root number is the sign of the functional equation of the L function. It's not simply a simple function of the rank. If the root number is negative, then the rank has to be odd. Then the rank has to be positive, because then the L function has to vanish at the center of the functional equation, and then the Birch-Swanston-Dyer conjecture says that the rank is positive, but it's not just a simple function of the rank.
I see.
It can be computed from the data of the curve, like not just a discriminant, but some other things, but not. I don't think it's that simple a function of the rank. Anyway, that's another thing to check. I'm just trying to understand what the machine actually learned. Whether it really learned the rank or something simpler. It may have learned some simpler thing, as in the case of the class numbers of real quadratic fields, where it could be that it just learns to compute whether it's divisible by 2 or 3 or 4 primes. And that's something that you can easily check. Anyway, that's the point of this discussion, to see what it is that the machine actually learns.
Right, that's right. Yeah, even the root numbers, or I mean here rank and root numbers are not easy to compute straightforwardly, but somehow this logistic regression could learn the numbers. That's quite interesting.
Yeah,
thank you. Yeah, thank you for
the rank is very, very difficult to
Can I add one comment?
Oh, yeah, sure.
Yeah, sure. I mean, the statement in the slide is exactly the parity conjecture. So, yeah. So it is proved under the finiteness of Shah. So basically, you can believe it. And for me, if machine can distinguish rank 1 or 2, then I would be very surprised. Yeah, that's
Yeah, 1 or 2. Yeah, and then the expert's name is the Alvaro Robledo. I mean, Alvaro told me that if a machine can distinguish rank 1 and 5, then that would be very.
That would be fantastic. Absolutely fantastic.
Yeah, or 2 and 3. Yeah, that's right.
Absolutely, absolutely.
Yeah, but that's the like in the list of to-do list. I mean, in the to-do list. Okay, thank you. And then let me move on. Now, I want to talk about Sato-Tate distributions. So C is a smooth projective curve of genus G defined over Q. And then for each prime P, where C has a good reduction, we define this zeta function. Here, nk is the number of points on C over this finite field. Then it is well known that the zeta function can be written in this form. And then the denominator is fixed, so we are interested in the numerator. And this numerator is a polynomial of degree 2g with the constant term 1. That's a well-known fact. Then an example, if C is an elliptic curve over Q, then the L polynomial has this form. Here AP appears again. Okay. And in order to get, I mean, we do this normalization in order to get a nice symmetry. Then actually the L polynomial after this normalization has this form. So this is a reciprocal polynomial. So this coefficient and this coefficient are the same for A2, the same. Okay, again, this is a well-known fact. And the distribution of these coefficients over the set of good primes give rise to the invariance of the curve. And and then this is a very interesting problem. So let me make the problem more precise. So let's consider the set of primes p less than or equal to n. We just consider good primes. And then we are taking the summation of these powers and then divide it by the number of primes and take the limit. So if m is 1, of course, this is the average. M is 2, then it's the second moment. So we are calculating the mth moment so that we may see the distribution. If we know all the mth moments, then that describes the distribution of the numbers. So if you go to Andrew Sutherland's homepage, then you see the distribution for these elliptic curves. So I think we have time, so let me show you. Yeah, this is the curve x cubed plus x plus 1, and the histogram is this. So here n is now 2 to the 22. Yeah, and then moments appear here. Okay, so likewise, if we have this, it's x cubed plus 1. And this 2 to the 14, yeah, that's the capital N moments appear here. It converges, and then the moments converge to integers. As you can see, this is 3, this is 10, 35, etc. And amazingly, people recognize that there are only 2 different moment sequences. Even though there are infinitely many elliptic curves, there are only 2 different distributions. And that was the famous Sato-Tate conjecture. Now it's proven by Richard Taylor and his collaborators. And so 2 moment sequences are these. If the elliptic curve is a non-CM, then we have basically Catalan numbers. If this 1 to 5, 14, and then 42, yeah, these are Catalan numbers. And then if the elliptic curve is a CM, then we have these numbers. These are binomial, central binomial coefficients. But this is very interesting, or it's amazing thing. And then now it's proven. It is not only for genus 1 curves. If we consider genus 2 curves, then again we obtain the moment sequences like this. Okay, and how many different distributions do we get? It's known that conjecturally there are 34 different distributions for genus 2 curves. So, and then if we consider genus 3, then we obtain these moment sequences. And how many different distributions are there? Very recently, Fite, Cadolaya, Sutherland showed that there are exactly 410 Sato-Tate groups of a billion threefolds over number fields. So over Q, I think it is about, I don't know the exact number, but probably around 300 or something like that. Okay, and question? Not yet. So interestingly, the distributions of these coefficients from the L polynomials are related to random matrices. So we can generalize the Sato-Tate conjecture. The conjecture is this: the distributions of these numbers are asymptotically the same as those of the coefficients of characteristic polynomials of random matrices in the Sato-Tate groups. So these numbers and the distributions are actually the same asymptotically, the same as the coefficients of the characteristic polynomials of the random matrices. That's the conjecture. In genus 1 case, we may interpret the moment sequences as the moment sequences of the coefficients of the characteristic polynomials from SU2 for non-CM. And for CM, we have a normalizer of a U1 inside the SU2. So these are Sato-Tate groups. In general, if we consider this USP2G, then Sato-Tate group H is a compact subgroup of USP2G, and then it satisfies a certain set of axioms. And then if we consider Sato-Tate group H and give the hard probability measure on H, then because this is a unitary group and also symplectic group, The characteristic polynomial has this form. It is a reciprocal polynomial. And then we consider this gamma as a random matrix, and these coefficients will be considered as a random variables. Then we can consider this mth moment by computing this integral. And Sato-Tate conjecture says that actually we have this. That's the conjecture. So the generalized Sato-Tate conjecture says that given a curve, that's right, there exists a Sato-Tate group H. So that this is from random matrices or a Sato-Tate group, and oops. Yeah. And then this is coming from the curve. And we expect the identity is true. For example, if this curve will be associated with this Sato-Tate group because it has it is a non-CM, and the CM is associated with this group, and then this curve, the pole USP4, and then there is a certain group. I will not define these groups because of the time. And then even for genus 3, we have Sato-Tate groups. For genus 2 curves, these are the groups. Here, for this talk, the generic case is this USP4, and then we have this group, SU2 times SU2. And then here is the normalizer of the group. The U1 times SU2. And then because this is a normalizer, there is a certain matrix. And then we are considering the group generated by these. And then normalizer of this group, SU2 times SU2. So there are other groups. These are the list of the Sato-Tate groups for genus 2 curves. Now, question: can a machine distinguish genus 2 curves according to their Sato-Tate groups? We can ask this question. And a majority of genus 2 curves belong to the generic case. Oops. And a majority of non-generic curves belong to this. And we do not have enough number of curves to train a machine for the other Sato-Tate groups. For example, LMFDB has only 303 curves for this Sato-Tate group and only 144 curves for this group. Then the number is too small to train a machine. It should be much bigger than like 300. But based on the generalized Sato-Tate conjecture, we may use random matrices to train a machine and then show the curve data and then see if the machine can tell the Sato-Tate groups according to the curve data. It is trained by the random matrix data, and then we just use the machine to determine the Sato-Tate groups. But that may be an idea. So we did that in our experiment. So first, we consider generic case from the non-generic case. So these are from curves. We are having two coefficients from a curve for each prime, and prime is up to this number. So I think we got 200 primes. And then we want to see if the machine can tell if the curve belongs to the generic case or not. For this, we have enough number of data points. So we could use the curve data, then train a classifier. And interestingly, a naive-based classifier showed a very high precision, 0.99. It was surprising. And then distinguishing two non-generic cases. Here we are using data set from random matrices because we don't have enough number of curves available in the database. So we obtain this data set from random matrices and then showed the machine the data. Okay, and then after training classifiers using the data, this data set, we apply the classifier to the curve data available at LMFDB. And the result was that we got 100% accuracy. So there are only 300 curves, and the classifier could distinguish, 300 plus 303 plus 140 something. And then the naive-based classifier could distinguish these 303 curves belonging to this group with 100% accuracy. So it was surprising. Okay, so conclusion and outlook. So there are many other invariants we investigated. So if you are interested, please look at our papers. And then a machine can be trained to learn invariants in number theory. Yeah, I think that's clear from these experiments. Why do we see higher accuracies? So in my opinion, mathematical data is clean and clear without noise. So once something works, then you may see high precision. Then can we use a machine to study Gauss's conjecture or unboundedness of ranks of elliptic curves? I don't know yet, but it would be very important to interpret what a machine recognizes. Clearly, yeah, we have to understand what machine recognizes. Then we may go back to these problems or other problems and to develop new approach to the problems. And then understanding what a machine recognizes and laying down a mathematical foundation are research topics in mathematics for machine learning. So we wanted to apply machine learning to mathematics, but actually I think we have to develop or we have to have a strong mathematics for machine learning. So I think these two approaches are interacting, and they are we have to go back and forth. Hopefully, we'll see fruitful interactions in the near future. Okay, that's my final remark. And then, thank you for your attention.